Welcome back. And now let's ponder. Hopefully you made some good observations and drew some good conclusions. Faraday's law of induction basically brings together the different things that induced voltage depends on. Hopefully you realize that change is important. So when you had the magnet somewhere near the coil, the magnet itself did not cause a voltage, but when you moved it, there was a change in position. When you changed the field, or more specifically, you changed the magnetic flux, you caused an induced voltage. You also had the ability to be able to change the number of wraps in that coil. And when you change the number of wraps, basically what you're doing is you are multiplying the area that those field lines intercept. 1 circle versus 2 circles versus 3 circles, that's turning into a multiplier on that flux. So when we bring it all together, here's your equation for Faraday's law of induction. So the induced voltage in the coil, negative, that negative sign we'll talk about in a little bit, and the number of wraps in that coil, d phi dt, that's the rate of change of the magnetic flux. So your induced voltage is directly dependent on how you change that flux. And again, remember that magnetic flux is equal to a B dot A, or the calculus variety of that. So that changing flux could be a changing field. It could be a changing area. It could be a changing angle between that field and the area. Remember your dot product. Purpose of it is to put your area vector perpendicular to the plane of the area and the field vector in the same direction. Now I've written these equations, one calculus, one algebra, and really which variety you use depends on the situation and the nature of the change. So I want to take a look at a couple of examples. So here we have a circular loop, radius 0.5 meters, lies in a plane perpendicular to a uniform magnetic field. So then if I draw a loop, and so that area vector from that loop would be in a direction perpendicular. The plane of the loop is perpendicular to the magnetic field. So the way I've drawn it, the plane of the loop would be vertical. So then the external magnetic field would be horizontal. So B and A basically are in the same direction. You're reshaping this coil from a circle to a square in 0.1 second. So we have a change. Magnitude of the induced EMF. So then E equals negative N delta phi over delta T. I'm using the delta, the algebra version instead of the calculus version because my time period was given as a discrete time. And so then incrementally walking through this, negative N, well, there's only one loop, so N is 1. Delta phi over delta T, that's going to be a delta B dot A over delta T. What's changing is your area. So B is not, I'm going to pull B out. So then what I have is a delta A over delta T. We can see from the diagram that the dot product would be the cosine of 0 degrees, which is 1. And so then filling in values, negative, our B is 0.4 teslas. Change in area, that's going to be the area of your circle minus the area of the square. So that's going to be pi times 0.5 meters squared minus the area of the square. Well, we need the length of one side of the square. So over here, the circumference of the circle would be 4 times S, if S is the length of one of your sides of the square. So 2 pi times 0.5 meters is equal to 4 times S. That will give us an S of 0.79 meters. And so then the area of the square would be 0.79 meters squared. And then that's over the time period of 0.1 seconds. So that's going to give us an induced EMF of negative 0.67 volts. The negative is a directional thing. We'll get into right-hand rules and directional things in a little bit. So take a look at another example. Here we have a magnetic field varying as a function of time, and you've got an equation, a rectangular loop, and you're given the dimensions. And similar to the last one, B is perpendicular to the coil. So we could draw a diagram very similar for this one to the one we did on the last one. B and A are going to end up being in the same direction. Now, what we want to find is the induced current in the loop at 2.3 seconds. If we're going to calculate the induced current, we're going to get the EMF, and then somewhere along the line, we're going to take that EMF or that voltage, and we're going to plug it into Ohm's law. So, calculus version, because we're given an equation, EMF is equal to negative N d phi dt. N is 5, so I'm going to go ahead and put that value in. d phi dt, well, that's the derivative of B dot A dt. If we think about what's changing, the area is constant, but the field is changing. So I can pull that area out. So I'm going to get negative 5 times the area dB dt. So that's going to be negative 5 times the area. The derivative of our field equation, that's going to give us 0.066 T. And so now we want to evaluate and find the induced EMF at 2.3 seconds. So that's going to be negative 5. The area, convert to meters, 0.03 meters times 0.02 meters times 0.066, and our time of 2.3 seconds. That will give us an induced EMF of negative 4.55 times 10 to the negative 4th volts. Now I can use Ohm's law. V equals I times R. So that's going to be our negative 4.55 times 10 to the negative 4th volts is equal to I times the resistance, and our resistance is 0.2 ohms. That gives us a current value of 0.0023 amps. And again, there is a negative there, which would be a directional thing. One more example. We have a solenoid, 200 turns, diameter and length given, current given, drops to 0 in 0.25 seconds when it is shut off. Notice on each of these problems, there's lots of stuff given, and I'm taking the time to be able to write out exactly what is given, because you really need to keep that stuff straight, especially in one like this. So let's consider part A. You've got a circular loop that is placed inside the coil, such that the plane of the coil is perpendicular to the magnetic field. Calculate the induced EMF in the loop when the solenoid is shut off. So then let's kind of draw the orientation. Here is our solenoid, and now the loop has a radius of 3 centimeters. So then my loop would be like that, and we could picture this loop somewhere inside. I'm going to leave it kind of hang out there on the edge just so it's a little bit more visible. So we want to calculate the induced EMF. E is equal to negative N. If we're looking at using calculus or algebra, I would look at the discrete time period that we're given there, 0.25 seconds. I don't have any equations, so I'm looking at pondering the algebra version. Negative N delta phi over delta T. Extremely important you keep track of what goes with what, because now you have a solenoid and a loop. So negative N, that N is what you're inducing the EMF in, and what you're inducing the EMF in is the loop. So I'm going to subscript it with an L for loop. Delta phi, that would be a delta B dot A over delta T. Now B is caused by the solenoid, so that B for the solenoid, we derived that equation down the other day. That's going to be a mu naught small n times I, the dot product between B and A, based on your given that you have the perpendicular here between the plane of the area. That means that your area vector and B are going to be in the same direction, so that's cosine of 0 degrees. So we can drop that, that's 1. Area, that's the area where the flux is, and the flux is in the area of the coil. And so this area will be that loop, that coil. Now, backing up on subscripts, the little n, that's solenoid, the current, that's solenoid. And so then all of this is over a delta t. So now pulling things out of there, see I have negative n for the loop, mu naught is a constant, we don't need it in the delta. N for the solenoid, I'm going to rewrite that as capital N for the solenoid over the length of the solenoid, because that's what's given, the total number of turns and the length. I for the solenoid, I changes, so I will stay in the delta, but the area of the loop does not change, so it will pull out. So then I end up with a delta I for the solenoid over a delta T. Everything else was constant, everything else pulled out. And so then when we plug in numbers, notice as I plugged in numbers, I sequentially went through everything and plugged it in, but when I got to the change in the current, it is final minus initial, so that's 0 minus 2 amps. So the combination of that negative and the negative at the beginning is going to give us a positive value for the answer. And so then in the induced EMF, we're going to get a positive 1.42 times 10 to the negative 4th volts. Part B. Hopefully we can squeeze it in here. Calculate the induced EMF in a circular loop of radius 8 centimeters that is placed around the solenoid when it is shut off. First of all, we want to ponder what this is going to look like. Our situation, we still have our solenoid, which looks way better than I drew just a minute ago, but now our loop is bigger. Our loop has a radius of 8 centimeters. Our solenoid has a radius of 4 centimeters. So that means our loop is sitting out here somewhere like that. Now, all along, our math is going to look very similar, except when we think about the flux. I'm going to kind of highlight and overlay on part A. When we think about this flux, that B dot A, for a solenoid, the only place that the flux is being established, the field is being established, is inside the solenoid. So then that B dot A, this area is just the area of the solenoid. So what's going to change is only that. So everything we have written in the long equation with numbers is the same, except right here, that value, I'm going to write it way down here off to the side. The radius of the solenoid, because you need the area of the solenoid there, your radius of the solenoid would be 0.04 meters. So everything you had written out there mathematically except the change in radius. And so in part B, if you crunch through those numbers, we're going to get an induced EMF of a positive 2.53 times 10 to the negative 4th volts. Now let's talk about that negative in Faraday's law. Negative n d phi dt. That negative is referred to as Lenz's law, the only sign I believe that has its own special law. Hopefully in the investigation you recognized that that induced direction did change based on whether the magnet was moving towards the coil or away from the coil, or what pole of the magnet you had and what direction it was moving in. That negative basically means that your induced EMF opposes the change that caused it, or our slogan, fight the change. Whenever you induce an EMF, it will always be in opposition to whatever the change is. Meaning, if your flux is increasing, you will induce a magnetic field that tries to oppose that increase, so that induced EMF will be opposite the magnetic field that is in place. If your flux is decreasing, then that induced magnetic field caused by the EMF, we'll do right-hand rules in situations here in just a second, that induced field will support the existing magnetic field. Now let's consider the direction of the induced current in the wire loop when it is dropped. So here's our situation in the first part. Here is our loop. We're going to drop it. So it's going from a location up here where there is no flux to when it moves down a little bit further into here where there is a flux that is there. So we do have a d phi dt, which means we will induce an EMF, and if we have an EMF in the loop, we will have an induced current. Okay, so when we go to here, there's no flux. Here there is some flux. So we are increasing the flux. Lenz's law, the negative, we fight that increase. So then we're going to set up a current that fights the increase in the flux. Okay, so we have B dot A, we have our flux. What we want to set up is a current that opposes that flux. My field is going this way. I don't want to support that. I want to oppose that. So we want to set up a field from the coil in that direction. To be able to set up a current from the coil in that direction, if I wrap my fingers around, my fingers, if I have a current in that direction, in a clockwise direction, I will set up a magnetic field that opposes that, and I will fight the change. So our induced current and our induced EMF would be in that clockwise direction. In part B, as the loop passes through the field, well, here we have the loop somewhere in the midst of the field, and it's moving, say, from here down to here, but it's staying within the field. If it's staying within the field, say at that location it has a certain flux, a little bit further down it has a certain flux. I probably should have drawn the field a little bit larger. But the point I'm trying to make here is as it's moving through the field, every field line that exits the loop, another one enters the loop, so there is no change in flux. And if there is no change in flux, then the induced EMF or the induced current in the coil is going to be zero. You have to have change to be able to induce an EMF. In part C, we want the induced current in the loop as the loop exits the field. So here we have our loop right there, and we're moving our loop to here. So when we start, we have a flux, and when we end, our flux is equal to zero. That means we do have a change in flux, and we do induce an EMF or a current. Now, our change, because we want to fight the change, our change goes from having a value to having nothing. So fighting the change will be actually supporting the magnetic field that already exists there. So then I want to set up a current in my loop that will set up a magnetic field that's coming out at you. And so then I would have to wrap my fingers here and set up a current in that direction to be able to cause a magnetic field out. So then the induced current, the induced EMF, are going to be in a counterclockwise direction to fight the change and support the field that is there. Now, let's consider another situation. I would encourage you to pause the video and take a minute and move through the right-hand rules on each of these situations, pondering what the change is and whether you're supporting it or opposing the change based on the increase or decrease, and then we will talk through these. So on A, you have a current that is moving over here in a direction to the right, and you have the loop, and you're pondering what you are inducing in this loop. Well, let's consider the change. Our current is increasing, so if I can squeeze in our equation here, negative n d phi dt, this increasing current is producing a magnetic field. If we consider the magnetic field that this is producing, I put my thumb in the direction of the current. Up here where the loop is, my fingers go into the board. And so I have a magnetic field from that wire into the board up there. This is increasing, so that means this magnetic field is increasing. And if that magnetic field is increasing and we have the negative of Lenz's law, we fight the change. We don't want to support that. We want to oppose that. So I'm going to set up a current in my coil in that counterclockwise direction so that the coil produces a magnetic field coming out of the board to fight the change. And so then counterclockwise direction, I induced, or the EMF would be in that direction. Part B, current is going over to the right side and the current is decreasing. If we consider the direction of the magnetic field from that current, thumb points that direction over to the right. On the bottom of the wire, my fingers wrap into, and so here we have the field from a wire into that loop. Now, our current is decreasing, so this magnetic field is decreasing. If this magnetic field is decreasing, fighting the change will be fighting the decrease, so we will want to go in that same direction. So my thumb stays in, and I will induce a current in a clockwise direction to be able to fight that decrease in the magnetic field. Part C, loop over there, current here, current is constant. Right away, if we have a current constant, we're going to produce a current field, mu naught I over 2 pi r. If we produce a constant field, there is no change, and if there is no change, then we don't induce anything. So 0, nothing induced there. Part D, my electric current is increasing in an upward direction, and so my thumb points up. My magnetic field over here will go into the board. This is increasing. We fight the change. So the field caused by the wire is into. We don't want to support that. We want to oppose that. So I flip my thumb out and my fingers will wrap to give a current around in this direction. So that induced current will be counterclockwise.